Recently, satellites monitoring the Sahara captured a site that shouldn't exist. Pools of deep blue water have suddenly appeared right in the middle of the world's most famous desert. Satellite imagery reveals the extent of the flooding, documenting submerged palm trees and flooded infrastructure surrounded by miles of shifting sand. Filling a basin of this size in a hyper-arid region requires hundreds of millions of gallons of water, appearing almost overnight. This sudden geographic shift forces us to look past our basic assumptions about the stability of extreme environments. The traditional climatic baseline of the Sahara is defined by its hostility to moisture. In a typical year, vast stretches of the interior receive mere fractions of an inch of rainfall, levels so low that they are practically immeasurable. This lack of water bakes the desert floor into compacted mudplates, becoming nearly as unyielding as concrete. So, what force could be powerful enough to override this established state and bring millions of gallons of water deep inland? Answering that requires pulling back from the ground and analyzing the meteorological data that tracks moisture moving through the atmosphere. The cause was a rare, massive low-pressure system that successfully breached the desert's arid atmospheric defenses. This map tracks the atmospheric mechanics. Swirling currents created a direct corridor, pulling oceanic moisture deep into the continental interior. As the system stalled, precipitation spiked, dropping more water in just 48 hours than the region sees in several years. It's a reminder that even the driest environments are not invincible. They can be completely overridden by concentrated atmospheric events. While this storm feels like an anomaly, looking back through climate records shows that a flooded Sahara was once the standard. During a period known as the African Humid Period, this entire region was defined by massive megalakes and dense vegetation. Early human populations documented this wet era in rock carvings. They lived alongside hippos and crocodiles in sandstone caves that are now surrounded by dust. This model displays the primary driver of that shift. A slight wobble in Earth's orbital axis relocated the global monsoon rainbelt, pulling consistent rainfall across the entire Sahara. As the orbit shifted back, the rainbelt retreated, and the lush landscape dried out in a remarkably short window of time. Today's sudden lakes act as a real-time echo of that watery, highly dynamic past. When these rare floods occur, life responds immediately. Dormant seeds finally hit water, sprouting into vibrant green trees in the middle of a rocky valley. But the intense, relentless desert heat means these lakes will evaporate quickly, leaving the basin dry once again. Meteorological data suggests that the frequency of these extreme, temporary weather events is on the rise as global climate patterns shift. These anomalies show that our current predictive models must account for a landscape that is becoming increasingly volatile. The Sahara's sudden transformation demonstrates how quickly even the most established landscapes can shift when the right conditions align. Our maps represent only a single moment in time for a planet that is constantly cycling through different geographic identities. To understand the invisible forces currently altering the planet, subscribe and join our investigation. Because in order to truly see the Earth, we have to look at how it moves today, rather than just relying on how it appeared yesterday.